Okay, so first we will sketch the wing chord and the tail chord. So imagine this is the wing mean chord, and this wing is mounted to the fuselage at a certain angle. So let's imagine that this is the fuselage reference line. The angle at which the mean wing chord is mounted to the fuselage is IW, and we can identify a point where the resultant aerodynamic force is exerted, and this resultant aerodynamic force can be split into drag force on the wing and lift force on the wing. There is also a turning effect, so we will write that as MAC for the wing. Now this aerodynamic center is vertically separated from the center of gravity of the aircraft by a distance CG. So since I have already sketched an arrow to represent the drag, we should understand that the relative wind will also be in the same direction, because this is how drag is defined. Okay, so basically the relative wind will be parallel to this orange line. So I can define the angle of attack which is experienced by this wing. Okay, so this is the free stream velocity, and the angle formed between this relative wind and the chord line is the angle of attack. So this is alpha W, and the angle that the fuselage reference line makes with the relative wind is alpha FRL. So from here, one of the things that we can notice is the angle of attack is equal to the angle at which the wing is mounted plus alpha fuselage reference line. So that alpha fuselage reference line is equal to alpha W minus IW, which is obvious from the figure. Now we will sketch the tail section in the similar way. The fuselage reference line is just going to extend, and towards the end of this fuselage reference line, the tail would be mounted. So let's say that this is the mean chord of the tail, and we can identify the aerodynamic center of the tail where the resultant aerodynamic force is exerted on the tail. So let's say this is the point, the aerodynamic center of the tail, and there will be a drag force on the tail and lift force on the tail, and a moment about the aerodynamic center of the tail. And let's label the vertical separation between the aerodynamic center of the tail and the center of gravity of the aircraft as ZCG tail. So the first thing that we should realize is that the tail is downstream of the wing in this example, and because of that, the tail is going to see the free stream at a different angle. The wing is going to push the airflow downward. This is known as downwash. So the tail is going to see the relative wind at a different angle. So if this is the vector which represents the relative wind seen by the wing, because of downwash, the tail is going to see this relative wind at a different angle. Okay, so it will be turned slightly downward. So you can imagine that the tail is going to see V prime instead of V. And this angle by which the relative wind rotates for the tail is called the downwash angle. It is represented by the epsilon. So this is your downwash angle. And so this dt and v prime are going to be parallel to one another, although that doesn't seem to be the case in my sketch here. But you should understand that the drag has to be parallel to the local relative wind. So this dt and v prime are parallel to one another. Same direction. Okay, so let's focus on this tail section now. And let's say this is the fuselage reference line, and this is the tail mean chord. And so this was your relative wind seen by the wing. The relative wind seen by the tail is going to be turned downwards. So let's say this is the relative wind seen by the tail, and this is your dt. And in this example, just because I've already sketched it in this way, let's imagine that this is the aerodynamic center. Okay, so this is where the resultant force is exerted. The lift is going to be normal to the drag, so this is lt. So from our discussion of the geometry of the wing, we know that this angle is equal to alpha fuselage reference line. Okay, same as this angle here. Now this v prime is v rotated downward. Okay, so there is a reduction in alpha FRL. So when you measure the angle between this v prime and the fuselage reference line, you will find that this angle is going to be equal to, so basically the angle between this v prime and the fuselage reference line, this angle will be equal to alpha fuselage reference line minus downwash. Okay, because it is rotated downward, so minus the downwash. Now we know that the opposite angles will be equal to one another, so this angle will be equal to this angle. And okay, so let's sketch a vertical line here. So I'm interested in finding the component of lift and drag along this green line. So I want to find the vertical component as well as the horizontal component. The horizontal component is along the fuselage reference line in this example. So which is the reason we are actually discussing all this and trying to relate the angles to one another. Now lift and drag make a 90 degrees, and this vertical dashed line and the fuselage reference line, they also make 90 degrees. So this is the common angle, which means this angle is equal to this angle. Okay, so in other words, I have argued that the angle between the lift and this vertical line is equal to alpha fuselage reference line minus the downwash. So now that we know the angle that the drag makes with the fuselage reference line and the lift makes with the vertical, we can calculate the components of lift and drag along the vertical and the horizontal directions. So let's consider the lift first. The component of lift in the vertical direction is going to be LT cosine of alpha FRL minus downwash. And why are we bothered about this? The reason is we want to find the moment, right? So we want to find the moment created by this force about the center of gravity. So imagine that there is a perpendicular component of lift So that lift multiplied by the distance between the lift and the center of gravity is going to give us the moment. And this distance between the center of gravity and the aerodynamic center of the tail is known as the tail moment arm, and we will label it as LT. This was also stated in our previous lecture. So this distance is LT. It's called the tail moment arm. So the force times the distance, LT, will give you the moment. Now we have to think how this moment is going to rotate the aircraft. So you can see from the sketch here that this vertically upward pointing force will turn the aircraft downward. That's a negative moment. So this will give a negative contribution. And what about the effect of the horizontal component of the lift force? The horizontal component is going to be LT sine of alpha FRL minus epsilon. And now the distance, the vertical distance between this lift and the center of gravity is z cgt. So we have to multiply by z cgt. And how will this try to turn the aircraft? This will turn it upward, right? So that means we will put a positive sign here. So that's the contribution from the lift. Now similarly, we should obtain the moments due to the drag. So the vertical component of drag is going to be dt sine alpha FRL minus epsilon. The distance is LT. And the vertical component of drag is going to try to rotate the aircraft downward. So that will be a negative contribution. And similarly, let's write the moment due to the horizontal component of drag. Horizontal component of drag is dt cosine alpha FRL minus epsilon. The vertical distance between the aerodynamic center and the center of gravity is z cgt. So this horizontal component of drag is going to be pointing in this direction. So that will try to turn the aircraft downward, right? Downward. Okay. So that means again the contribution is going to be negative. Now here we will make some assumptions which will help us to simplify this equation for the moment about the aerodynamic center, moment about the center of gravity. So the assumptions are as follows. We will assume that this z cgt is very small in comparison to the tail moment arm. Okay, apply the following assumptions. And we should also assume that the angles are very small. Okay, angles are small, and the drag on the tail is very small in comparison to the lift. And we will also assume that this moment about the aerodynamic center of the tail is small. So how do these assumptions modify this equation? Let's see. So if the angle is very small, then cosine of the angle is simply going to be equal to 1, and sine of the angle is going to give us 0. So 0 here. And we have already said that dt is small and z cgt is small. So we are multiplying two small quantities. So we can also neglect this term. And we have already said that the moment about the aerodynamic center of the tail is small. So this is also equal to 0. So we are left with only one term, which is moment about the center of gravity caused by the forces acting on the tail is equal to minus tail moment arm times the lift on the tail. Okay, so we obtain a very simple equation at the end. Okay, so the moment caused by the tail, I'm going to skip writing CG because we understand that we are concerned with moment about the center of gravity. So moment caused by the tail is equal to minus LT. Now, what is LT? LT is equal to CLT times half rho VT square times ST. Okay, so this comes from the definition of the lift coefficient. And we also know that coefficient of moment is equals to moment divided by half rho V square SC. So please note that Vt and V are different. So the V I have written here, this is the free stream velocity which is seen by the wing. The S I have written here is the planform area of the wing. And this C is the wing mean chord. So when we define the moment coefficient, we are using the velocity, area, and the chord of the wing. Whereas the Vt here is the velocity which is seen by the tail, and St is the planform area of the tail. Okay, so go back to this equation and divide mt by half rho v square sc equals to minus lt. Now so there is a lift on the tail. I'll come to that, but because I have divided the left hand side by half rho v square sc, I will also divide the right hand side by half rho v square sc. And instead of LT, I'm going to write CLT half rho V T square ST. So this is equal to minus LTST divided by SC half rho Vt square divided by half rho V square times CLT. So this ratio, LT multiplied by ST divided by SC, this is called the horizontal tail volume ratio. Tail volume ratio. And as you can see, the term inside this curved brackets is the ratio of dynamic pressures. So this is the ratio of dynamic pressures. And this is also known as the tail efficiency or tail efficiency. It is denoted by eta. Okay, so you should call this eta. So my question is, for the geometry that we have sketched, which of the following is true? Is eta going to be greater than 1, eta going to be less than 1, eta equal to 1, eta equals to 0? What do you think? It depends on the location of the tail, but if the tail is behind the wing, the tail efficiency is going to be less than 1. Okay, the reason is that, see, by the time the airflow reaches the tail, because of the friction with the wing and the other parts in between the wing and the tail, the air has slightly decelerated. So this Vt will be less than V. Because of that, the tail efficiency will be less than 1. If the tail is put in front of the wing, in that case the tail efficiency will be greater than 1 because the velocity seen by the tail will be greater than the velocity seen by the wing. Okay, so there are some aircrafts in which you will notice that okay, if this is the wing and if this is the vertical fin, then the horizontal fin or the horizontal tail um, may be located actually near the nose. Okay, so for such aircrafts the tail efficiency is going to be greater than 1 because Vt is greater than V. But for the case that we are discussing, since the horizontal tail is after the wing, by the time the airflow reaches the horizontal tail, it has slowed down. Okay, so Vt will be less than V. So the tail efficiency is going to be less than 1. Okay, but again, when you are solving the problem, if the tail efficiency is given to you, then you should use that value. If it may be given as 1, right? So we may be ignoring the contributions of drag, and in that case, you may say that the magnitude of velocity seen by the wing is equal to the magnitude of velocity seen by the tail. So in that case, tail efficiency will be equal to 1. But strictly speaking, if the horizontal tail is after the wing, then eta will be less than 1. If it is before the wing, it is greater than 1. Now, when you put the tail in front of the wing towards the nose of the aircraft, this structure is known as canard. The physics is the same, only the location is different. So it is identified by a different name. So I can now write the moment coefficient because of the tail is equal to minus VH. VH is the horizontal tail volume ratio, VH, times eta times CLT. Is equal to CL0 T plus DCL T D alpha T alpha T. Okay, now this is nothing new. This is just the equation for the lift as a function of angle of attack. So if this is the CL of the tail and plotted as a function of the angle of attack seen by the tail, then since it's based on an airfoil, you can imagine that the lift as a function of angle of attack will be a straight line. So that is the equation of a straight line. Now here, when I write the equation like this, the alpha that is written here is called the geometric angle of attack. So in this equation, alpha t is the geometric angle of attack. Now I could also write the equation in terms of the absolute angle of attack. So what is absolute angle of attack? Absolute angle of attack is the angle of attack measured relative to the zero lift angle of attack. So let's say we have an angle here. This is say 5 degrees. Okay. So that 5 degrees I have written there is the geometric angle of attack because this is being measured from 0, right? This is being measured. This is 5 relative to the origin. Okay. So this is the geometric angle of attack. But I could measure this angle relative to the zero lift angle of attack, right? This is the zero lift angle of attack. So if the value of this zero lift angle of attack is, let's say, minus 2 degrees, so minus 2 degree is its value relative to the origin, then this angle of attack, this one, will have a value of 7 degrees in terms of the absolute angle of attack, right? So this is 7 degrees absolute angle of attack. 7 degrees because we are measuring this angle relative to this minus 2, right? So we have decided to refer to minus 2 degrees as the starting point. Okay, so when you measure the angle from the zero lift angle of attack, then that angle is your absolute angle of attack. So instead of sketching CLT as a function of the geometric angle of attack, I could also sketch CLT as a function of absolute angle of attack. So when I do that, the plot will always pass through the origin. When I express the x-axis as absolute angle of attack. Okay, because we are defining 0 at a point where the lift is 0. Okay, so what I'm trying to say from all this story is that the equation I have written here, this equation, can also be written as CLT equals to d CLT d alpha t, provided that this alpha t is the absolute angle of attack. So I don't need that CL0t. Okay, so long story short, this is the equation for the lift coefficient of the tail. Now, let's think about this alpha t, the angle of attack, which is seen by the tail. Now, this angle of attack seen by the tail, I think we've discussed this in the last lecture as well, but I'll recap it here. So let's say this is the tail section, this is the fuselage reference line, and this angle is the angle at which the tail is mounted to the fuselage. So this is your IT, and we know that this V prime, okay, it makes an angle here which is equal to it's equal to alpha fuselage reference line minus the downwash, right, that we have already talked about today. And we also know that this alpha fuselage reference line is alpha wing minus IW, right? So this is equal to alpha W minus IW minus epsilon. Now, the angle of attack is the angle between the local relative wind and the chord line. Okay, so this is the alpha t. So we can say that alpha t is equal to this angle plus this angle, which is alpha W minus IW minus epsilon plus IT. In other words, now I will rewrite this alpha t as a combination of those other angles I have written there. All right, we have actually, let's just go to this equation. Okay, so we have CMT equals to minus VH eta CLT. Now CLT is dCL t d alpha times alpha t. Now this slope will be written in the shorthand notation. Okay, and alpha t is equal to alpha W minus IW minus epsilon plus IT. Okay, so this is the CMT. Okay, so we need to go a little further than this. We are making progress. Now let's think about this downwash angle. Okay, how are we going to obtain it if we want to do some calculations, right? So again, this downwash angle, let's say it varies linearly with the angle of attack seen by the wing. So the downwash is created by the wing. Okay, so we can model this downwash as some constant value plus the rate of change of downwash with respect to the angle of attack seen by the wing times the angle of attack seen by the wing. Downwash angle is given by this formula. which means the slope of downwash angle with respect to the angle of attack is equal to 2 times dClW d alpha w over pi arw, and in short notation this becomes 2 cl alpha w divided by pi arw. So in a given problem you will be able to calculate the downwash angle if you know the lift slope and the aspect ratio of the wing. So this is equal to minus vh eta cl alpha t alpha w minus iw minus epsilon naught. So epsilon naught is the downwash at a zero angle of attack. Okay, so this 0 here in the subscript means the angle of attack is 0, minus d epsilon d alpha w plus it plus it. Now we need to rearrange the terms as usual. Okay, so we need to regroup the terms in the expression that I have just written. Let's do that. CMT equals to right, let's see. So we have this is equal to minus VH eta CL alpha T. In the brackets I have minus IW plus IT minus epsilon naught, and again I have minus VH eta CL alpha T minus, not minus, alpha W minus d epsilon, yeah, d alpha W. So this is equal to the tail volume ratio, tail efficiency, lift slope of the tail times IW plus epsilon naught minus IT minus VH eta CL alpha T 1 minus d epsilon d alpha W. This is what we obtained. Now why did I put it in this form? The reason I put it in this form is I want to compare it with the linear relationship between the moment coefficient and the angle of attack. Okay, so we know that CMT is equal to CM0T plus CM alpha T times alpha points. So we want to compare this expression with the linear relation between the moment coefficient due to the tail and the angle of attack. So when we make this comparison, what do we see? We see that this first term, this is your CM0T, and this is the slope. Okay, so this is CM alpha T. So it helps to separate them out because the slope and the offset have two different effects, as you have seen in the past, right? The slope will determine whether this is statically stable or not, and the offset has to do with the angle of attack at trim point. Okay, so that is the reason we are always separating the offset and the slope. So I can write now that CM0, all right, so CM0T is equal to eta times VH times CL alpha T IW plus epsilon naught minus IT. And then CM alpha T is equal to minus eta VH CL alpha T times 1 minus d epsilon d alpha W. This is what we got. When you calculate the CM0 for the entire aircraft, CM0, it will be equal to Cm0 caused by the tail plus Cm0 caused by the wing plus Cm0 caused by the fuselage, plus any other contribution from other aircraft components if you want to include it. So that's why this equations that we have obtained for individual parts are later going to be combined to come up with the moment coefficient for the entire aircraft. In the same way, Cm alpha will also be combination of Cm alpha tail plus Cm alpha wing plus Cm alpha fuselage plus other things if you want to include, although the effect of other components will be very small, right? So the dominant players here are the tail and the wing, and then maybe a little bit from the fuselage. Right, so this is the numerical example that I want to discuss, and in homework 2 there will be problems not exactly same as this one, but if you understand this you will be able to do those other problems in homework 2. Homework 2, which has not been issued yet, but I'll release it soon. Okay, so that is another reason I would like to see you get started on homework 1 immediately if you have not done that already. All right. So it says the wing fuselage pitching moment characteristics of a high wing single engine general aviation airplane follow along with pertinent geometric data. The equation is given. So in addition to solving this problem, I also want to discuss this problem in general, okay? Because as we discuss this problem, it will clarify or help us to review many concepts we have discussed so far. All right, so this is a single engine, so most likely the engine is at the nose. Okay, so this is the aircraft. So maybe there is a propeller here. And it's a high wing. High wing means if this is the fuselage. Okay, so here is the cockpit. Then high wing means the wing is mounted like this. Okay, this is high wing configuration. And general aviation airplane follow along with pertinent geometric data. Okay, so we are given the equation for the moment coefficient about the center of gravity. So C M C G WF is equal to minus 0.05 minus 0.0035 alpha. So WF means wing and fuselage. So the combined contribution of wing and fuselage is described by this equation. That is what it means. Okay. So just for the sake of discussion, if I make a plot of Cm versus alpha, then alpha equals to 0, then Cm Cg negative 0.05. So let's say this is my negative 0.05, and this will be negatively sloped because it's a negative, right? And when alpha equals to 0, Cm is okay. So it will be something like this, right? So this is our Cm about the center of gravity due to the wing and fuselage, where alpha is the fuselage reference line angle of attack in degrees, and WF means wing fuselage. Okay. So the planform area of the wing is given. The span length is given 35.9 feet. The wing mean chord, this is the location of the center of gravity. The aspect ratio of the wing is given, although we could have calculated it because we know SW and BW, so it was not necessary to give this. Then the lift, this is CL alpha, right? So this is the slope. Okay, so you need to get used to reading the shorthand notation. So the lift slope from the wing and fuselage is given 0.07 degrees. The wing setting angle, or the angle at which the wing is mounted to the fuselage, is given, and the value of lift at a 0 angle of attack is also given. Okay, so your goal is to estimate the horizontal tail area, so ST, and the tail incidence angle IT. So this is the angle at which the tail is mounted to the fuselage, so that the complete airplane has the following pitching moment characteristics. yeah, so far we have only been dealing with the pitching moment, okay, because we are only discussing whether the forces will rotate the aircraft downward or upward, right? So about its lateral axis. So this is pitching moment. So we want the total moment coefficient about the center of gravity to be this. Okay, so in other words, this cm cg wing fuselage, which is given to us, plus cm cg due to tail, should be combined to give us 0.15 minus 0.025 alpha. So if you sketch it, then let's see. So when alpha equals to 0, you get a positive 0.15, right? So if you set alpha equals to 0, you will get cm equals to 0.15. So let's say this is your 0.15, and then it's a negative slope, means it will be, and you can see that it's a steeper slope, right? So maybe they will intersect somewhere. These two will intersect somewhere. Okay, anyways, that intersection is not important. The important thing here is, from the practical point of view, what you need to appreciate here is that because of the tail, the aircraft is able to fulfill the desirable characteristics for static stability, right? So the wing and fuselage only made the slope negative. Okay, only made the slope negative. You can see that. But the intercept was also negative, right? We want a positive intercept so that the aircraft can be trimmed at a positive angle of attack. So how is that being achieved? That's being achieved from the tail contribution, you see. Because when we add the tail contribution, when we add this, you see the intercept has become positive. It's now 0.15. And another thing to notice here is that we are adding the tail to make the slope steeper, which means the aircraft will be more statically stable. So if you look at this slope of the moment coefficient because of the wing and fuselage, it's minus 0.0035. Compare that with minus 0.025, which is a bigger number, right, in magnitude. So the tail in this way makes the aircraft more statically stable, and it also helps to achieve the trim point at a positive angle of attack. So in order to do that, the question is, what should be the tail area and what should be the angle at which the tail should be mounted to the fuselage? So this is what the question is asking. Okay, and this is how you should imagine this question being applied in reality. Okay, so it's not just math. You have to imagine how this will actually apply to the aircraft. All right, is in degrees is the wing fuselage horizontal tail contribution. Assume the following with regard to the horizontal tail. So the tail moment arm is given, tail efficiency is given, aspect ratio of the tail is given, and the lift slope of the tail is given. Okay, so how are we going to find this? All right, we will write down. Hang on. So basically, we need to find some properties of the tail here. Okay, so the equation for the moment coefficient of the tail that we had written is going to be used, obviously. Okay, so that means cm cg tail equals to cm cg wing fuselage tail minus cm cg wing fuselage. Now this also means cm, I'm going to stop writing cg, okay, because we are only dealing with the moment about the center of gravity here. So this also means cm0 t equals to cm0 wing fuselage tail minus cm0 wing fuselage. So this is going to be important for us. And another thing is cm alpha tail is also equal to cm alpha wing fuselage tail minus cm alpha wing fuselage. So these two relations are going to be useful. So let's find the value of this cm0 for the tail. cm0 for the tail is equal to, now the difference is going to be cm0 wft. cm0 wft is 0.15 minus cm0 wf. So that's going to be minus 0.05. This is going to give us 0.2. Eta is given to us. CL alpha tail is given to us. Okay. IW is also given. IW is also given. We need to find this, and we need to calculate this epsilon naught and VH. We need to calculate these two. So okay, so there are many unknowns here, right? So 1, 2, 3 are unknowns here. So this equation alone is not going to be sufficient. Let's write another equation. So we also have the equation for Cm alpha t. So let's first find the value of this Cm alpha t. Cm alpha t is equal to Cm alpha wft, which is minus 0.025, right? So this is minus 0.025 minus Cm alpha wf, that's minus 0.0035. What will be the difference? Minus 0.0215, and this is going to be power degree. And I have the equation for Cm alpha t, right? The equation is minus eta Vh Cl alpha tail 1 minus d epsilon d alpha. So this is one of the equations that we had obtained before we started on this example problem. So we have minus 0.0215 equals to minus eta Vh Cl alpha t 1 minus d epsilon d alpha. Now here let's track what is known and what is not known. This eta is known, right? So this is given as 1, as you can see here. Again, this Vh is not given, but we need that Vh. So, and Cl alpha t is given, and the slope is not given. So again, this is an equation with two unknowns. All right, so somehow we need to make use of these equations that we have. Okay. All right, so let's deal with these epsilons and the slope of this epsilon. So if you go back to what we have written today, you know that this downwash is equal to 2Cl divided by pi ar. Okay, so we already stated this today. Now this downwash at zero angle of attack is equal to 2 times Cl at zero angle of attack divided by pi times ar, and this is the aspect ratio of the wing and the lift coefficient of the wing. So that's 2 times the lift coefficient at zero angle of attack is given to us. Okay, so that's 0.26 divided by pi times the aspect ratio of the wing, 7.3 given. So you can compute a number there. By this equation and obtain the downwash angle, it will be in terms of radians. Okay. Now you are given this IW in terms of degrees, and you are also given the IT. Oh, IT you have to calculate. Yeah, IT needs to be calculated. So just keep that in mind. Okay, so CL, so this is in degrees. So better to convert this radian into degrees. Okay, so convert it into degrees so that the units of the angles are consistent. So we'll come to that in a little bit. Okay, so regarding this equation now, we have found the value of epsilon naught. IW is given. CL alpha t is given. VH is not given. So we need to find VH. And my plan is to obtain VH from this equation that we got after processing this expression for the moment slope due to tail. Okay, so to do that, you need to find the value of this d epsilon d alpha. Now again, we have already stated that d epsilon d alpha is equal to 2 Cl alpha divided by pi ar, 0.07 divided by, so 1 degree is, so pi 180 degree is pi radian. So 1 degree is pi divided by 180. Aspect ratio is 7.3. Okay, and you will get a number here. Of course, this is d epsilon by d alpha, so there are no units, right? Because angle is being divided by angle. But it will be correct only when you enter this dCl alpha, not dCl alpha, only when you enter this Cl alpha as per radian. Okay, then only you'll get the correct answer, because these equations only work when the angle is in terms of radians. So you'll get a number here. And what is that number? All right, so VH is 0.453. So you now have this 0.453, and you can obtain the value for IT. Okay, so you can solve for IT. We also need ST. Okay, now for that, you can use the definition of VH, I think. VH is ST times LT divided by SC. So LT is given to us. The tail moment arm is 14.75. We want to find ST. VH is 0.453 divided by S, which is 178, times C, which is 5. So from this, you can find the value of ST. So the idea is that if you now design this tail with whatever this number you get here, that area, and if you mount it at whatever angle you get here, you will be able to obtain this stability curve, which will significantly improve the static stability in comparison to the case where you had only the wing and the fuselage. And it will also allow you to trim the aircraft at a positive angle of attack. Okay. What you can notice here, guys, is that the slope, Cm alpha, is a very small negative number. And here, in comparison, it is a bigger negative number. Now, you can imagine that instead of being negative, it could also have been positive, Maybe this could have been Cm CG wing and fuselage could have given you minus 0.05 plus 0.0035 alpha. Let's say there are some other design issues which forces you to have a positive slope here. But that's okay, right? Because when you combine it with the tail contribution, when you combine it with the tail contribution, you may be again able to get this number. So in that case, the value of this IT and ST will change. Okay, so the idea is that overall the aircraft needs to be stable, not like component wise, because component wise there may be other constraints that we may have to. Let's have a look at this pair of equation. Now we know that we want this to make a positive contribution, right? So we want this to be positive, correct? So for this to be positive, see, this factor is going to be positive, this is going to be positive, this is lift slope, which will be positive. And now let's say that the wing is mounted on the fuselage at a positive angle. Okay, and that is usually the case, right? We see that the wing is, so if this is the fuselage, then the wing may be mounted like this. So that's a positive wing setting angle. And this is positive also. Okay, let's imagine this is also positive. Maybe it is negative. Okay, whatever be the case, the point is that you want to make this positive, and in order to make it positive, it will help if this IT is negative, right? IT is negative. So if this IT is negative, then you'll get negative, negative, and this will be positive. So overall, this CM0T will be positive. Okay, so which means that if you look at the tail section of the aircraft, you will most likely see that this horizontal fin or the horizontal tail is mounted downward. Okay, and you can actually explore this. You can Google search the tail section, and you will notice that the horizontal tail is mounted like this. I don't think you will be able to find a photo in which the horizontal tail will be mounted like this. So the reason it is mounted at a negative angle is so that this will give a positive contribution to CM0. Okay, so that's one thing that you can explore and realize. The other thing is, in addition to making sure that this CM0 is positive, we also want to make CM alpha negative, right? Now that can be done by controlling several factors. You can control the value of VH, or you can control the value of this tail efficiency. Okay, this CL alpha is most likely going to be positive. And yeah, similarly, this one also will have a contribution which will favor making this CM alpha negative. But you can imagine that you can really control the value of CM alpha by applying this VH. Okay, so VH equals to ST SC. So by making the tail area larger, or by increasing the distance between the center of gravity and the tail, you can increase the value of this VH, which will make the aircraft more stable.